Geologists have mapped them. Scientists have published on them. Tour guides lead visitors through the smaller ones every day. But there is one thing about these cave systems that keeps appearing in the literature, quietly, without commentary, and nobody in any official capacity has ever explained it. Not like rivers, not like cracks in rock, like trees. And when you start pulling that thread, the questions don't stop coming. Mammoth Cave in Kentucky is the longest known cave system on Earth. As of the last published survey, it has over 420 mapped miles of passages. That number keeps growing. New corridors are found every few years. When cartographers first began systematically mapping it in the 1800s, they noticed something they didn't have language for. The passages didn't branch the way erosion normally branches. They didn't widen and then split the way rivers do. They didn't crack outward from a fracture point the way rock typically fractures under pressure. They branched hierarchically, one large corridor, then several medium ones extending from it, then smaller ones from those, then smaller still, each branch thinner than its parent. Each terminal passage ending in a narrow point. That's not erosion. That's not hydrology. That is, structurally, the architecture of a vascular system. Now, the standard explanation for cave formation is this. Acidic water percolates through limestone over millions of years, dissolving the rock and carving passages. The passages form where the water finds weaknesses, where fractures exist, where the rock is softer. That explanation is not wrong. It's the mechanism. The chemistry is real. The timelines are real. But the chemistry of dissolution doesn't produce hierarchical branching. Water, left to find its own path through fractured rock, produces something closer to a web or a maze. You get complexity, yes, but not hierarchy. Dendritic patterning, the specific tree and root structure, requires either a template or a directing force. In biology, that template is the organism itself. A tree's root system branches the way it does because the tree is directing nutrients, routing water, expanding into available space with intention encoded at the cellular level. When geologists find dendritic drainage in rivers, there's also a clear explanation. Gravity. Water flows downhill, and the land surface dictates where it goes. The hierarchy comes from the watershed. The high ground drains to the low ground in a predictable cascade. But cave passages form underground, often horizontal or with minimal slope. There is no watershed. There is no surface gradient explaining the hierarchy. So here is the question that the literature never quite asks directly. What was the template? If dissolution created these passages over millions of years by following something, what did it follow? What was already there? In the limestone, shaped like a tree waiting to be dissolved away. There are three possible answers in the scientific literature. None of them are fully satisfying. And the fourth answer, the one that isn't in the literature, is the one we're going to spend the rest of this video sitting with. Limestone is a sedimentary rock. It forms from the accumulated remains of marine organisms, shells, coral, microorganisms, compressed over millions of years under ancient seas. The key thing to understand about limestone is that it is not uniform. It has layers. It has zones of differing porosity. It has, embedded within it, the physical record of whatever was deposited in that ancient marine environment. When researchers look at the zones of highest porosity in limestone, the zones where water most readily penetrated and dissolution was fastest, they sometimes find something interesting. The organic matter content is higher. The zones where cave passages preferentially formed correspond to zones where there was more organic material compressed into the rock. This is documented. This is published. The standard interpretation is that ancient organic material, compressed into the limestone, left behind slightly more porous, slightly more chemically reactive zones. And so the acidic water followed those zones. Fine, reasonable. But here's where it gets interesting. The Mammoth Cave region of Kentucky sits on what geologists call the Mammoth Cave Plateau. The limestone there was deposited during the Mississippian period, roughly 330 to 340 million years ago. At that time, the area was a shallow tropical sea, not a forest, not land at all. There were no trees, there were no roots, there was water, coral, shells, microorganisms. So the organic material in that limestone is marine in origin, not terrestrial, not roots. Shells and coral skeletons and single-celled organisms. And yet, the passages branch like roots. Now, there are researchers who point to a different formation window. The caves themselves, the actual passages, didn't form during the Mississippian. They formed much later, beginning perhaps 10 to 15 million years ago and continuing into geologically recent times. By then, there was land, there were forests. There were, in fact, trees growing on the surface above the limestone, and roots, particularly the deep tap roots of large trees, can reach down through thin soils and into the fractured upper surface of limestone bedrock. They secrete carbonic acid as they grow, which etches into the rock. They die and leave channels. Some researchers have proposed that ancient root systems pre-carved a template in the upper limestone. That dissolution then followed those root channels downward, enlarging them, extending them, eventually producing the full cave system. This hypothesis has a name. It's called the hypogenic dissolution via biotic precursor model, though that term isn't universally used. It remains a minority position in speleogenesis literature. The mainstream position is still that fractures in the rock, structural weaknesses from tectonic stress, guided the water. Roots are considered a minor factor, if acknowledged at all. But when you actually overlay the branching geometry of the passages with what we know about root architecture, something is difficult to ignore. The branching ratios match, not approximately, closely. There's a measurement in biology called the bifurcation ratio. It describes how many smaller branches emerge from each larger branch in a hierarchical system. In healthy root systems, that ratio typically falls between 3 and 5, meaning each branch tends to produce 3 to 5 sub-branches. In Mammoth Cave's passage network, the published survey data shows an average bifurcation ratio of approximately 3.7. Nobody in the literature has commented on this directly. If this were only Mammoth Cave, you could explain it as a local anomaly, a specific geological context producing a specific result. But it isn't only Mammoth Cave. Carlsbad Caverns in New Mexico, one of the most studied cave systems in the world, formed by a different process than Mammoth Cave, sulfuric acid dissolution from below rather than carbonic acid from above. Formed in different rock, at a different time, in a completely different geological context. The passage plan at Carlsbad also branches dendritically. The bifurcation ratios are similar. Lechuguilla Cave, also in New Mexico, considered by many cavers to be the most beautiful cave in America, extends for more than 145 mapped miles. It formed hydrothermally through volcanic processes interacting with sulfuric acid. A completely different mechanism again. Same branching structure. Jewel Cave in South Dakota, Wind Cave in South Dakota, which has its own remarkable peculiarity we'll come back to, Fisher Ridge Cave System in Kentucky, separate from Mammoth but geologically adjacent, the Greenbrier Valley Cave Systems in West Virginia, all dendritic, all with similar bifurcation ratios, all formed by different mechanisms in different rock types, in different states, over different time periods. When you find the same pattern across different mechanisms, different materials, different times, the mechanism is no longer the explanation. The mechanism is how the pattern was produced, not why the pattern exists. There's a principle in geology called convergent morphology. It means that different processes can produce similar shapes when they're working within similar constraints. Riverbeds and cave passages can look similar because water moving through a medium under gravity or pressure follows the same fluid dynamics, regardless of whether the medium is air, soil, or rock. That's one explanation for the branching. The physics of fluid flow naturally tends toward hierarchical distributions because that's the most efficient way to move material. Water flowing through rock, given time, will self-organize into efficient networks. This is actually a real field of study. There's a body of mathematics around optimal transport networks, and biological systems like root systems and lung bronchioles and vascular networks converge on the same geometries because those geometries are efficient. So one answer is, these caves look like roots because efficiency selects for the same shapes everywhere, in every medium, at every scale. Biology didn't design the tree root, physics designed it. And physics designed the cave the same way. That's a clean answer, a satisfying answer. But it runs into a problem. If fluid dynamics alone produce these shapes, then caves should be much more uniform than they are. The variations in branching geometry, in passage width, in corridor height, in the specific microarchitecture of individual passages, should smooth out toward a universal optimum. They don't. Each cave system has its own signature, its own style of branching, its own characteristic passage shape. Carlsbad looks like Carlsbad and not like Mammoth, even though both are dendritic. In biology, we have a word for when a system follows universal efficiency principles, but also carries its own unique expression of those principles. We call it a genome. Wind Cave in South Dakota deserves its own chapter. It was first recorded by European settlers in 1881. A rancher named Tom Bingham heard a whistling sound coming from a small hole in the ground, approached it, and the wind coming out of the hole was strong enough to blow his hat off. Wind Cave gets its name from this phenomenon. The cave breathes. When the atmospheric pressure outside is lower than the pressure inside the cave, air flows out. When pressure outside is higher, air flows in. This is known, documented. The cave acts as a barometer, its breadth a function of pressure differentials between the underground system and the surface. But here's what's less discussed. Wind Cave has been mapped to over 150 miles of passages. It is one of the densest cave systems ever documented, meaning it has more passage length per square mile of surface area than almost any other cave system on Earth. The passages are tightly packed. They run in every direction. They connect to each other in multiple places. And Wind Cave is not fully mapped. Surveys estimate that what has been mapped represents perhaps 5% of the total system. If that estimate is accurate, Wind Cave extends beneath the Black Hills of South Dakota as one of the largest cave systems on Earth, possibly larger than Mammoth Cave. Now, Wind Cave is also dendritic, but because it's so dense, so tightly interconnected, the dendritic pattern is almost obscured. The branching is there, but it's layered on top of itself, dozens of overlapping hierarchical networks stacked in the same rock. Researchers who study Wind Cave have proposed that it formed in phases, different dissolution events at different times, each creating its own dendritic network, all in the same limestone body, all now interconnected. That's possible. That's probably what happened. But it raises a question nobody's answered to full satisfaction. Why does the same rock body, under different dissolution events separated by millions of years, consistently produce the same branching geometry? If the geometry were being imposed by fractures in the rock, fractures from tectonic stress, then multiple dissolution events would follow those same fractures, and you'd get overlapping but aligned networks. What you'd expect is corridors that run parallel to each other, that run along the same structural grain of the rock. Wind Cave's passages don't do that. They go everywhere. There's a small body of researchers, going back to at least the 1960s, who noticed the branching anomaly and wrote about it directly. Not in mainstream geology journals, in speleology journals, cave research publications, the specialist literature that most people never read. A researcher named Arthur Palmer, who spent decades studying Mammoth Cave and wrote what is still considered the definitive textbook on cave formation, acknowledged in a 2007 paper that the passage geometry of dendritic cave systems was not fully explained by existing dissolution models. He didn't frame it as a mystery, he framed it as an area requiring further study. That's how the anomaly is typically handled in the literature. Not suppressed, not argued against, just noted as incomplete, and moved past. There's a separate thread that comes out of the 1990s from researchers working on what's called fractal geometry in geological systems. The idea that natural systems, from coastlines to mountain ranges to river networks, exhibit self-similar patterns at different scales, the same shape, repeated from macro to micro. When researchers applied fractal analysis to cave systems, they found something that confirmed and complicated things simultaneously. Cave passage networks are fractal. They exhibit self-similarity across scales. The large-scale branching pattern is repeated in the smaller-scale branching pattern, which is repeated in the micro-scale passage texture. This is interesting because fractal geometry in natural systems is well understood. Rivers are fractal, coastlines are fractal, root systems are fractal, lung bronchioles are fractal, snowflakes are fractal. The underlying explanation for fractal patterning in all of these systems is the same: iterative processes, repeated rules applied at progressively smaller scales, produce self-similar outcomes. In rivers, the iterative rule is water flows downhill, eroding the path of least resistance. Applied again and again, it produces fractal drainage. In root systems, the iterative rule is encoded in the plant's DNA. Each growing tip follows the same growth algorithm, producing the same branching pattern at every scale. In lung bronchioles, the rule is the same: maximize surface area within a constrained volume. What's the iterative rule in caves? The dissolution model gives you a mechanism but not a rule. Acidic water follows the path of least resistance, but that should produce a maze, not a fractal. A fractal requires the same algorithm to operate at every scale. For caves to be fractal, something had to be applying the same rule at the micro scale as at the macro scale. Something had to be templating the geometry all the way down. Those micro channels in the cave wall, the ones that look like tiny root hairs, nobody has fully explained what made those. The limestone beneath the eastern and central United States is old, older than the continent's current form, older than most of the landmarks we associate with American geography. The Mammoth Cave limestone was laid down when what is now Kentucky was near the equator, when North America was a different shape, when life on land was new. And here's something that the standard formation timeline doesn't address clearly. The surface above Mammoth Cave, the forested plateau where the park now sits, has been forested for a very long time, millions of years, with trees, large trees, deep-rooted trees. There's a growing field called paleohysology, the study of ancient root systems. Researchers working in this field have found fossilized root traces in Devonian and Carboniferous rock going back over 350 million years. The first true forests on Earth appeared roughly 385 million years ago, and those ancient trees had root systems. The first forest in the rock record is called Archaeopteris. It was a large tree, up to 30 meters tall. Its root system has been reconstructed from fossils. It was extensive, deep-reaching, dendritic. Now, the limestone beneath Kentucky was not forming when Archaeopteris was alive. The limestone is from the Mississippian. Archaeopteris is from the Devonian, slightly earlier. They don't perfectly overlap, but the principle doesn't require a perfect timeline. It requires that at some point, over the millions of years during which these cave systems were forming, there were forests on the surface. And there were. The question researchers haven't asked in print, at least not directly, is whether the entire dendritic geometry of these cave systems might represent the ghost of ancient root systems, not any single forest, not any single species, but millions of years of successive forests, each one pressing its root template into the limestone, each dissolution event following a biotic map. The rock as a kind of negative space, the caves as the shape of what was once alive. There's no paper making this argument directly. There are papers touching each individual piece. the fractal geometry, the bifurcation ratios, the role of organic material in dissolution pathways, the documented influence of surface root systems on upper cave levels. The conclusion nobody has drawn is the one that connects all of it. Mammoth Cave receives about 2 million visitors per year. They walk the lit passages, they look at the formations, they hear the guided explanation. Acidic water, limestone, millions of years. That explanation is true. It's just not complete. Here's what we know and what we don't know, and why the gap between them matters. We know these cave systems exist. We know how many miles they extend. We know the basic chemistry that formed them. We know they're fractal. We know their bifurcation ratios are within the range of biological systems. We know organic material in the rock correlates with passage location. What we don't know is why the geometry is hierarchical when the mechanism predicts a maze. We don't know what applied the same branching rule at every scale. We don't know whether successive ancient forests left a template that dissolution then followed. And we don't know how much is still down there. The karst landscape of the United States, the limestone terrain under which cave systems form, underlies about 40% of the country east of the Rocky Mountains. Most of it has not been systematically explored. Most of it is not accessible. Most of it is simply down there. The caves beneath America are shaped like tree roots. No one has fully explained why. The most honest thing the literature gives us is a shape, a pattern, something that keeps appearing in the dark, hundreds of feet beneath the surface, in rock laid down long before anything we recognize as modern civilization. The pattern doesn't prove anything. It just keeps being there. There's a video on this channel about another underground anomaly, one that connects to a completely different part of this question. It's on screen now, and if you made it to the end of this one, subscribe. The next video goes somewhere you won't expect.